The final thing we're going to look at is how empirical and molecular formulas for compounds can help chemists figure out what exactly is the identity of an unknown compound. So imagine that you're looking through your grandparents' house and you come across in the garage this weird unknown chemical. And the question is, what is the chemical? And chances are, because it's in the garage, you don't want to start drinking it or something, or even smelling it. Worst case scenario, you'd be dead. And best case scenario would probably just smell weird or be suspicious. So one of the ways that chemists get paid a lot is through identifying compounds. And we can use these techniques so far and see how this works out. Remembering that compounds are always in the same proportions. So NaCl is always table salt. It's never NaCl2 or Na2Cl. You can actually relate this to how much things weigh or what the mass is. So we're going to talk here a little bit about percent by weights or percent by mass, all right? All practical purposes for this class, weight and mass are the same. If you get into physics, it's not quite that same. The ethanol we looked at earlier, you'll be able to do this by the end of the chapter. It's 52.13% carbon, it's 13.15% hydrogen, and it's 34.72% oxygen. So you're probably like, how did they get these numbers? And that's a really great question. People, for example, that are trying to have low sodium diets might want to know the percentage of sodium in the foods they eat, because if you are trying to keep sodium low, you don't want to have a lot of sodium. These percentages can be helpful for a whole bunch of different things. If you want to find the weight percent of an element in a compound, the basic way is to first find the molar mass of the compound, put it in the bottom, the denominator, and in the top part, you'll put the grams of the element in the compound. So let's do an example with nitrogen dioxide, all right? And if you're going to find the weight percent of nitrogen and oxygen, the first thing, once again, is to find the molar mass. Now, very roughly, oxygen about 16 grams per mole, and there's two of them, so 16 times 2 is 32. Roughly, nitrogen is 14 grams per mole, so 32 from the oxygen plus 14 for the nitrogen, roughly NO2 is 46 grams per mole. You can do a better job to the hundredths place with your calculator and periodic table than I can do off the top of my head, but roughly the number that goes in the bottom is going to be 46. In the top, you want to put the grams of that element in the compound. So if this was oxygen, NO2, there's two oxygens, and 2 times 16 is 32. For percent oxygen, you would put 32 grams roughly in the top and 46 grams, which is the molar mass, in the bottom times 100%. And that would be the weight percent of oxygen. Now for nitrogen, you only have one nitrogen. That's about 14. So the weight percent of nitrogen would be 14 grams in the top and about 46 grams in the bottom, the molar mass times 100%. That's what you want to do. Now, you can do a better job and sig figs and all that kind of stuff than I just did. Here's an example of with water. All right, we saw earlier that the molar mass of water, 18.02 grams per mole was the molar mass. We'll put that in the bottom. Weight percent of oxygen, one oxygen, 16.00 grams. So the weight percent, 16.00 divided by 18.02 times 100%. Weight percent of oxygen, 88.79% oxygen. So going back to the NO2 example, here are better sig figs. So I said the molar mass was going to be about 46. 46.01 is even better, all right? And so for percent nitrogen then, you'd have the 14.01 grams of one nitrogen divided by the molar mass times 100%. Weight percent N, 30.45%. For oxygen, notice it's 2 times 16. That's because NO2 has two oxygens. So you put 2 times 16 divided by 46.01 times 100, 69.55%. Notice that your percentages of all the elements together should be 100%, and those look really good. Also, if you have 1% element and there's only another percent element, then 100% minus that number would be an alternative way to find the percent of the other one. So for example, if you had percent nitrogen, 30.45, you could also go 100 minus 30.45 to get that 69.55%. So lots of kind of cool ways to do that stuff here. Let's say that you wanted to figure out percent nitrogen in nitrogen monoxide, NO. All right, and the molar mass, which is what MM stands for, 30.01. So molar mass goes in the bottom, percent nitrogen, 1 nitrogen goes in the top. You'd have 14.01 divided by 30.01 times 100, and that number, 46.68%. Answer B. And again, to find percent oxygen, instead of 1 times 14.01 in the top, you'd go 1 times 16.00, the 1 oxygen. Divide by the molar mass times 100%, that would be the percent oxygen. You could, of course, also go 100 minus 46.68%. So one way that chemists can distinguish compounds from another is through the mass percent or the weight percent. So for example, in NO2, the weight percent of nitrogen, 30.45%, but for NO, 46.68%. So that is one method that can be used to find one compound from another. But there's a problem. So this is an example of testing yourself for the weight percentages of nitrogen and oxygen in dinitrogen tetraoxide. Now, NO2 and N2O4 are quite different compounds. There's not a lot of similarities to them. But notice mathematically that NO2 times 2 is N2O4. So for example, for the percent nitrogen, if you were doing that calculation, it would essentially be 46.01 times 2 in the bottom. And for nitrogen, you'd have 14.01 times 2 because it's N2. The punchline of the test yourself question is that the percentages of nitrogen and oxygen in N and O and NO2 are the same as the percent nitrogen and percent oxygens in N2O4. Same percent composition. So it is not enough to know the percent composition or weight percent or mass percent. All these things mean the same thing. You have to know more than the percentages. And that's what makes this stuff a little tricky. There's lots of examples where compounds will have the same mass percents, like NO2 and N2O4 here. They're especially in organic chemistry, that's very common. So we're going to start using the mole to take us to the next level.